Welcome to this video on the types of graphs, including their classifications and examples. We will begin with an introduction to the basic terminologies used in graph theory. A graph is a way to show connections between things. The things are called vertices or nodes, and the connections are called edges or links. The degree refers to the number of edges connected to a vertex. Examples of graphs include velocity time plots and maps showing routes and connections between locations. Graphs can be broadly classified into fundamental graphs and special simple graphs. Fundamental graphs include simple graphs, multigraphs, and pseudographs. Special simple graphs include complete graphs, bipartite graphs, and regular graphs. Let's explore the core concepts of these graph types. A simple graph is an undirected graph where a vertex is not connected to itself, and there are no multiple edges between any pair of vertices. If a simple graph has n vertices, the maximum number of possible edges is n times n minus 1 divided by 2. The sum of degrees of all vertices equals 2 times the number of edges. A multigraph is a graph in which 2 or more edges can connect the same pair of vertices. In a multigraph, loops may or may not be allowed. If loops are allowed, it is sometimes called a pseudograph. Multigraphs can be represented using an adjacency matrix where entries greater than 1 indicate multiple edges. A pseudograph allows both multiple edges between the same pair of vertices and loops, which are edges that connect a vertex to itself. In a pseudograph, a loop contributes a count of 2 to the vertex's degree, while each parallel edge contributes 1. The adjacency matrix can have non-zero diagonal entries for loops and entries greater than 1 for multiple edges. A complete graph, or Kn, is a simple graph where every pair of distinct vertices is connected by a unique edge. This means every vertex is connected to every other vertex. Properties of a complete graph include no missing connections, no loops, and no multiple edges. For n vertices, the number of edges is n times n minus 1 divided by 2, and the degree of each vertex is n minus 1. A bipartite graph's vertices can be divided into 2 disjoint sets, A and B, such that edges only connect vertices from different sets, not within the same set. Mathematically, for a bipartite graph, the vertex set V is the union of 2 disjoint sets, V1 and V2, where their intersection is empty. The properties of a bipartite graph include 2 disjoint vertex sets with no edges between vertices of the same set. Vertices in set A can have different degrees from those in set B. A regular graph is a graph where every vertex has the same degree, meaning the same number of edges, but not necessarily connected to all others. This is known as all equal connections. For a regular graph, the total degree is n times k, which equals 2 times the number of edges. A complete graph is n minus 1 regular, and a complete bipartite graph Kn, n is n regular. Examples include 0 regular graphs with no edges, and 2 regular graphs forming cycles. Next, let's look at the applications of these graph types in the real world. A simple graph example is a velocity time plot. In computer networks, a LAN where each pair of devices is connected by at most 1 cable is a simple graph. Multigraphs are seen in Google Maps when showing multiple routes between 2 destinations. In computer networks, 2 routers connected by multiple physical cables for redundancy or load balancing form a multigraph. A pseudograph example is a user liking their own post, a loop, on Instagram, or liking a friend's post multiple times, which are multiple edges. In networking, a server with a loopback interface and multiple VPN tunnels represents a pseudograph. A complete graph, or all connected, is like a WhatsApp group where every member can chat directly with every other member. This corresponds to a fully connected mesh topology in computer networks. In a bipartite graph, an example is people and movies, where an edge exists if a person would rewatch a movie. In client-server architecture, clients connect only to servers, not to each other, forming a bipartite graph. A regular graph represents all equal connections. For example, 4 friends sitting in a circle, each shaking hands with their neighbors, creates a 2 regular graph. In a ring topology, every computer is connected to exactly 2 others, making it a 2 regular graph. Now let's practice with some example problems in section 1. Example 1 asks for the maximum number of edges in a bipartite graph on 8 vertices. The solution involves partitioning the 8 vertices into 2 sets as equally as possible, 4 and 4, and multiplying the set sizes to find the maximum number of edges, which is 16. Example 2 asks, how many perfect matchings are there in a complete graph of 8 vertices? The solution utilizes the formula for the number of perfect matchings in Kn, which is n-1 double factorial, resulting in 1035 for 8 vertices. In Section 2, we will go through some GATE exam previous year questions, or PYQs. Our first PYQ is from GATE CSE 2003. How many perfect matchings are there in a complete graph of 6 vertices? The options are 15, 24, 36, and 60. Using the same formula, the number of perfect matchings in a complete graph of 6 vertices is 15. The next PYQ from GATE CSE 2014, Set 1, asks for the maximum number of edges in a bipartite graph on 12 vertices. The options are 36, 37, 38, and 39. To find the maximum number of edges in a bipartite graph on 12 vertices, divide the vertices into 2 sets of 6 each, 6 times 6, which equals 36. Thank you for watching this video. We hope you found this information about graph fundamentals helpful.